Okay, we're back for the second part of 5.1 notes. So this is 5.1 part 2. And we're going to build on our classical probability. So because classical probability is all hypothetical or theoretical, it's very important that we can determine the sample space or even just the size of the sample space in order to find probabilities. We have two main tools to help us with this: tree diagrams and multiplication rule of counting. So let's start with a tree diagram. It's a very basic visual way to envision all the possible outcomes. A graphic organizer used to list all possibilities of a sequence of events in a systematic way. Tree diagrams are one method for deducing the outcomes in a sample space. So you're going to see how a tree diagram over at the right. So the tree starts here, and then if there's only a heads and a tails, there's two possibilities, right, on the first tree. So this would be the first trial, so trial 1. And then after trial 1, you either had a heads to start from or a tails to start from. And then you still had a heads and tails on possibility on trial 2. So after 2 trials, you could have a heads and a heads on the first and a tails on the second. Or you could have had a tails on the first and the heads on the second. And they're different outcomes, right? And tails and tails. And then it says, be sure to make a vertical list at the right of the diagram with all the outcomes. So this is actually your sample space. This is going to help you visualize it, but this is actually your sample space here. So this is important to finish this last step. So it says an overhead ceiling fan with a light has 2 settings for the light, bright and dim, and the same fan has 3 settings for the fan, low, medium, or high. Construct a tree diagram to show the sample space for all possible settings. Okay, so we have, what do we say? We had bright and dim. So we have bright and dim. And then the second setting is low, medium, or high. So we have a low, a medium, and a high. And then we also have a low, medium, and a high down here. So our final sample space is basically all of the combinations of the 2 settings. So okay, so we could have bright and low, bright and medium, bright and high. We could also have dim and low, dim and medium, and dim and high. So there's 6 possibilities here for our sample space. Okay, so B at the bottom says define the event G. The fan is at least medium. At least medium means medium or high. At least means you start at medium and go higher. So medium or high. So let's star the ones that would satisfy this. That would be bright and medium. Let's do it over here. Bright and medium, bright and high, dim and medium, dim and high. So there's 1, 2, 3, 4. So we're going to write out those possibilities. BM, BH, DM, and DH. Okay, let's go ahead and flip the page. We're going to look at a little bit bigger situation. This one is, let's say we were going to have 3 children and we wanted to not predict, but see what are the possibilities of combinations. What could their biological sexes be? Assume falsely only male and female, and that each is equally likely. Okay, so we are going to look at, we have 3 children. So the first child I'm going to do in a red. So the child 1 could be male or female. The second child I'm going to do in blue. So that's child 1. So the second child could also be male or female. Male and female. So far we could have 2 males, 2 females, or combinations, right? And then the third child could also be male or female. So we could have male or female, male or female. This is child 3. We could have male and female. We could have male and female. So we're going to write out our full sample space. So we could have male, male, male. Or male, male, female. We could also have male, female, male. Or male, female, female. Those are all the ones where we had a male on the first child. And now we're going down to all the possibilities where we had a female on the first child. So we could have female, male, male, or female, male, female, or female, female, male, or female, female, female. So there are a total of 8 outcomes that could happen here. And I'm going to see that there were 2 outcomes for the first child times 2 outcomes for the second child times 2 outcomes for the third child. So it's 2 to the third or 8 outcomes. We're going to actually formalize this in a minute. So B says, what is the assumed probability of each outcome in the sample space? So these are each of my outcomes, and they each are 1 out of 8. It says list all outcomes in event H, where H is having at least 1 male. So at least 1 male. I'm going to circle above. So at least 1 male. There's at least 1 male. They had 3. They have at least 1 male, at least 1 male, at least 1 male. Now all of these down here, they have at least 1 male, at least 1 male, and at least 1 male. So only 1 got left out, right, where they had 3 females. It says, what is the probability of H? So there were 7 of the 8 outcomes that were at least 1 male. And that comes out to be 0.875 or 87.5%. The tree diagram above were 12 for 2 and 3 children, but would you want to do it for 6? Can you imagine how big this would you'd need a whole wall to do this. So no, not enough space, right? Not enough space or time. So we want to have more of a mathematical way to figure out how many items are in, how many outcomes are in our sample space without having to write them all out. So we're going to use something along this multiplication thinking here. Turn to page 141 and you will see the multiplication rule at the top. Is used to determine size of sample space. If a task consists of sequence of choices in which there are P selections for the first choice, Q selections for the second, R selections for the third, and so on, then we can multiply those possibilities to get the total number of combinations, okay? This rule helps find the size of the sample space. We don't actually know what the exact sample space is unless we actually work them out, but we at least know the size of the sample space. So for example 10, I'd like you to pause for just a minute and then calculate the sample space size for the following probability experiments. Now, you could go back for just a minute to we did the one with the children, but also if you went back to the one with the lights for the ceiling fan, you've got 2 outcomes for this setting, right? And then there were 3 outcomes for the 3 settings for the other, 3 settings for the other on the fan, the speed. And so that should tell us 2 times 3, there should be 6 outcomes. And we did find that over here, there were 6. Okay, so go ahead and pause your recording and work on those. Well, now we're back and we are going to formalize these because we're going to have 6 children and they each have 2 outcomes. So 2 outcomes to the 6th power gives us 64 outcomes in our sample space. It says you're going to randomly guess on a 10-question multiple choice quiz where each question has 4 options. So question 1 has 4 options times question 2, right? Question 3, all the way to question 10. So this is going to be 4 to the 10th, which is 1,048,576 outcomes. So they'd have to really guess good to do well in that as a guesser. You're going to toss a fair 20-sided die and then a fair 8-sided die. So that one's just 20 times 8, or 160. D. This time, the license plate picture has a steam engine. They all have that, but then there's 4 digits, right? Each of those digits, it says, can have repetitions are allowed, and they're just 4 digits. So we have anywhere from 0 through 9, which means there's 10 possibilities, 0 through 9, and they each have 10. So this is the same as 10 to the 4th or 10,000. The last one is talking about, we're going to select 3 cards from a standard deck, and we want to look at replacement and without replacement. So with replacement means that when we draw the card, we mark down what we drew, and then we put it back in the deck. So we could theoretically draw that card again. So that means all 3 cards have 52 possibilities. So 52 to the 3rd is 140,608. And then let's say we did without replacement, which means that we draw our card, set it aside. So the first card has 52 possibilities. The second card now only has 51. And the third card now only has 50. So this makes the number of possibilities 132,600 because that first card is no longer a possibility and then the second card is no longer a possibility. So we're going to do a little experiment. I would love for you to grab a die and a coin if you'd like. So I have a coin, a penny. It's dirty. There's the tails. We're going to look at this coin and die activity, or you can also go to the online dicefree.com and we're going to simulate this. We'll go there momentarily, but it says, how large is the sample space? So we are going to toss a coin. So the coin has 2 outcomes, right? Heads or tails. And then the six-sided die. So there should be 12 possible outcomes that we could get. And we are going to construct the sample space for these 12 outcomes. So we have heads and tails. And then we also have, we're going to flip the, we're going to roll the die. And so there's 1, 2, 3, 4, 5, 6. And then we're going to have 1, 2, 3, 4, 5, 6. And so our sample space, remember, is when we put it all together. So we have heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. So there are 12 outcomes. We can see them here, and that validates what we came up with up here. It says, what is the classical probability of tossing an H and a 1? So a heads and a 1. That would be 1 out of 12, which is also 0.083. So next up, I'd like you to go to the website. This is onlinedicefree.com. And we're going to momentarily look at this and do this experiment together. So we are going to go to that website so we can do our own experiment for some empirical data. You can see here at the website, it says that we're going to roll a die and we're going to flip a coin. Okay. Now, I would like to do this 12 times just to see, because our possibilities were 12 in our sample space. And it says technically, well, not technically, but classical probability says that 1 out of the 12 we should get an H and a 1. So let's go ahead and tally this. Let's do this 12 times. I'd like you to do it at home as well. So I'm going to roll my dice and flip my coin. So it looks like I got a 6 and a heads. I'm going to just tally on my page all the ones that I got. So I got a heads and a 6. And then, ooh, I got an H and a 1. That's pretty cool. And then I got a 5 and a tails, tails 5. So that's my third. I got a heads and a 2. I got a tails and a 2. Tails and a 3. That's 1, 2, 3, 4, 5, 6. That's 6. Ooh, I got another heads. A heads and a 1. That's exciting. A heads and a 3. And the tails and a 2. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 3 more. A tails and a 1. And a tails and a 6. And a tails and a 5. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, So let's just go back to, so you can see where I tallied these here. And you can see I tallied them here. It says how many trials of the experiment were H1 in the class overall. So of the 12 that we rolled, 2 were H1. How many trials of the experiment did the class make? 12. So what is the empirical probability? It's 2 divided by 12, or 0.167. Explain the difference between classical and empirical probability using these results. So classical means we should have had 1 out of 12, or 0.083, but empirical means we actually had 2 out of 12, or 0.1667, right? So we actually had more than what we should have had. So we could do this again, and let's say we did it again, and this time none of the 12 rules were an H and a 1 out of 12. So our empirical was 0 out of 12 this time. Okay, I'm making it up. Now I'm going to pretend that we did this again, and this time out of the 12 we had 3 out of the 12. So 3 out of the 12 would be 25%, right? 0.25. Then lastly, it says how many trials of the experiment were in H1 total? So we had 2, 0, and 3. So we had 5 out of 36 trials. We're adding our 12 from each of those. So 36 times total, right? So 5 out of 36 is 0.1389. And so you can see how it was close. It's a little high. Then it was 0, right? Very much lower than what it should have been. Then we went way up, and then it kind of went evened out again, right? So eventually, if we did multiple trials over this, we would get very, very close to the 1 out of 12 from the classical probability. Okay, you can see on page 145, it says, let's consider a simulation that was run of this experiment. So it says, how many trials of the experiment are simulated? And it looks like they ran 10,000. It says, does the simulation support our answer for part R? So you can say number of tosses. When you can see here, this is the first few tosses. There were some that were, and this is just counting the H1s, that were really high, right? And then they didn't have as many, then they had a couple more H1s, but then it actually evened out and evened out and evened out right about at that 0.083. So exactly what we thought. So this explains what we say is our law of large numbers down here. As a probability experiment is repeated over and over and over again, the proportion of times that a given event occurs in the empirical probability will approach its classical probability. So there's no such thing as the law of averages. You are not due to win no matter how long you stay at the slot machine or the craps table. And what does this mean for the gambling industry? It means that you may hit on the roulette table your number 3 or 4 times in a row, but eventually, if you kept playing on the long run, you're going to have just as many where you don't win. And so if you win, take your money and leave. That's the gambling responsibly. And the biggest thing is only only bet what you can afford to lose. I'm a statistician. I know very well my likelihood of winning is not very high. Okay, but you can go and have fun. It's a card game, it's a dice game, it's a spinning game. But you have to go in with the idea that you're only taking the amount of money that you're willing to lose. So if I take it 20 bucks, I'm assuming I'm losing all 20 and I have to be okay with that. But if I win some and I'm like, hey, I won a little bit, I'm taking it and I'm leaving, all's well that ends well. Just don't go back to the ATM, only take cash and that's it. We'll see you back for 5.2.